Far beneath the waves of the western Pacific Ocean, there lies a place of profound darkness and immense pressure, a world that has fascinated explorers and scientists for generations. It is a world almost beyond our imagination, a scar in the Earth's crust so deep that it could swallow our tallest mountains whole with miles to spare. The Mariana Trench is not just a geological feature, it is a testament to the dynamic forces that shape our planet. This is the Mariana Trench, the deepest known point on our planet, located east of the Mariana Islands and stretching across a remote part of the Pacific Ocean. For centuries, humanity has gazed up at the stars, dreaming of exploring other worlds. Yet the mysteries beneath our own oceans remained largely untouched until the modern era. Right here on our own planet, there exists a realm more alien and less understood than the surface of the moon. The deep sea, and especially the Mariana Trench, is a frontier that challenges our technology and imagination. It is a place of silent, crushing blackness, where the weight of the ocean above is 1,000 times greater than what we feel on land. The pressure here is so intense that it would crush most human-made objects. This immense pressure has shaped a unique and fragile ecosystem, one we are only just beginning to understand. Life here has adapted in extraordinary ways, thriving where it seems impossible. The sheer scale of the trench is difficult to comprehend. It is the deepest, darkest and most mysterious part of the ocean. It stretches for more than 2,500 kilometers, a vast curving canyon hidden from the sun, running parallel to the Mariana Islands. At its deepest point, known as the Challenger Deep, the seafloor rests nearly 11,000 meters below the surface. This spot is the lowest known point in any of the Earth's oceans. To put that into perspective, if you were to place Mount Everest at the bottom of the trench, its peak would still be covered by more than a kilometre of water. The trench dwarfs even the greatest mountains on land. This incredible depth makes exploration extraordinarily difficult and dangerous. Only a handful of manned and unmanned vehicles have ever reached the bottom. For a long time, it was thought that no life could possibly survive in such a hostile environment. The trench was believed to be a barren wasteland. But as we have developed the technology to peer into this abyss, we have found that it is not empty at all. Remotely operated vehicles and deep-diving submersibles have revealed a hidden world. It is a world teeming with strange and wonderful life, creatures that glow in the dark, survive on chemical energy, and defy our expectations of biology. Our fascination with the Mariana Trench goes beyond simple curiosity. It is a living laboratory for scientists seeking to understand the limits of life and the history of our planet. It is a place of incredible scientific importance, holding clues about the very origins of life on Earth and perhaps on other planets. Some scientists believe that life may have started in environments just like this. The creatures that live there have evolved remarkable adaptations to survive the extreme conditions, offering insights that could lead to new discoveries in medicine and biotechnology. Enzymes from these organisms are already being studied for industrial and pharmaceutical uses. The geology of the trench itself tells a story about the powerful forces that shape our planet, where one tectonic plate is slowly being forced beneath another in a process called subduction. This process is responsible for earthquakes, volcanic activity, and the recycling of Earth's crust. It is a dynamic and powerful place, a true frontier on our own world that beckons us to explore its secrets. Each expedition brings new surprises and challenges. But today, the race to understand the Mariana Trench is not just about science. It is also about national pride, technological achievement, and strategic interests. It has become a new stage for global competition. Countries vie for the prestige of reaching the deepest depths and for the potential resources that lie below. Nations, particularly China, are now investing heavily in the technology to reach and operate in these crushing depths. China's recent advances have made it a leader in deep-sea exploration. They are drawn not only by the promise of knowledge, but also by the lure of valuable resources that lie on the seabed, metals and minerals essential for modern technology. This new deep-sea gold rush raises important questions about ownership, environmental protection, and the future of this pristine wilderness. The balance between exploration and conservation is more critical than ever. As we venture deeper into this dark world, we are faced with a great responsibility to protect one of the last untouched places on Earth. The story of the Mariana Trench is not just about discovery, it is about stewardship, wonder, and the future of our planet. The journey from the sunlit surface of the ocean to the bottom of the Mariana Trench is a descent through a series of distinct and dramatically different worlds, each with its own unique physical and biological characteristics. These layers, or oceanic zones, are not just boundaries of depth. They are crucial to the functioning of our planet's largest ecosystem. Each layer is defined by how much sunlight it receives, its temperature, and the immense pressure that builds with every meter of depth. These factors shape the types of life that can survive and the roles they play in the ocean's complex web. The first zone we encounter is the one most familiar to us, the epipelagic zone, or the sunlit zone. It extends from the surface down to about 200 meters where sunlight can still penetrate. Here, sunlight enables photosynthesis, making this zone the primary producer of the ocean's oxygen and the foundation of marine food webs. This zone is warm, bright and bustling with the marine life we know and love, from playful dolphins and majestic whales to vast schools of fish and colourful coral reefs. Phytoplankton thrive here, supporting nearly all higher life forms in the ocean. It is the engine of the ocean where most of its life is concentrated. The epipelagic zone is also vital for regulating Earth's climate as it absorbs large amounts of carbon dioxide from the atmosphere. As we sink deeper, we leave the light behind and enter the mesopelagic zone, often called the twilight zone. This layer stretches from 200 meters down to 1,000 meters, where sunlight is too weak for photosynthesis but still present in faint traces. The sunlight here is faint and fades quickly into darkness, creating a unique environment where day and night blend together. The pressure increases dramatically, reaching up to 10 times what it is at sea level. Temperatures drop sharply and oxygen levels decrease, making survival a challenge. Life here begins to look more alien. Many species have adapted to the low light and high pressure with specialized organs and behaviors. Creatures like the strange oarfish, the longest bony fish in the world, and the beautiful but predatory sea angel drift through the dim light, relying on stealth and bioluminescence to hunt and avoid predators. Many animals in this zone have developed large eyes to capture the last glimmers of sunlight, and some have even begun to create their own light through a process called bioluminescence, a chemical glow that will become essential for survival in the deeper zones. The twilight zone also plays a key role in the global carbon cycle, as many organisms migrate daily between layers, transporting nutrients and carbon. Below 1,000 meters, we plunge into total unending darkness. This is the bathypelagic zone, or the midnight zone, which extends down to 4,000 meters. No sunlight ever reaches here. The only light here is the light that creatures make themselves. Bioluminescence is used for communication, camouflage, and hunting in the pitch-black water. The pressure is now immense, over 100 times the pressure at the surface, and the water is near freezing, typically around 2 to 4 degrees Celsius. Yet life persists, with organisms evolving slow metabolisms and unique adaptations to survive. This is the home of the eerie Magnapinna squid, with its long, elbow-like tentacles, and the famously unattractive blobfish, whose gelatinous body is perfectly adapted to withstand the crushing force. Many species here are scavengers, feeding on the remains of organisms that drift down from above. In this world of darkness, bioluminescence is used not just to see, but to attract prey, startle predators and find mates in the vast, empty blackness. The bathypelagic zone is a frontier of scientific discovery, with many species still unknown to science. Finally, we reach the deepest parts of the ocean, where the environment becomes even more extreme. The abyssopelagic zone, or the abyss, lies between 4,000 and 6,000 meters. The zone covers more than half of the ocean floor and is one of the least explored regions on Earth. Here, the seafloor is a vast flat plain covered in a thick, muddy substance known as marine snow, a constant shower of dead organic matter from the upper layers of the ocean. This slow rain of nutrients is the primary food source for many abyssal creatures. Life is sparse, but it is here. Organisms have adapted to the cold, high-pressure and low-nutrient environment, often living long lives and growing slowly. Below this, in the deep ocean trenches like the Mariana, we enter the Hadal zone, a realm of crushing pressure and perpetual darkness. Named after Hades, the Greek god of the underworld, this zone begins at 6,000 meters and plunges into the deepest chasms, reaching depths greater than Mount Everest is tall. The pressure is over 600 times that at the surface, a force so great it would crush most conventional machines instantly. Temperatures hover just above freezing, and the water is saturated with dissolved minerals from hydrothermal vents. It is a world we once thought to be barren, but we were wrong. Even here, unique organisms thrive, some feeding on chemicals from hydrothermal vents, others scavenging what little organic matter drifts down. These hidden layers of the ocean are not just mysterious, they are vital to the health of our planet, supporting life in ways we are only beginning to understand. The creatures that inhabit the deep ocean zones are a testament to the incredible adaptability of life. In these lightless depths, evolution has crafted some of the most bizarre and fascinating organisms on Earth. In the twilight zone, where light is a fading memory, animals have evolved extraordinary features to survive. Lanternfish, for example, use rows of photophores to communicate and camouflage themselves, making up one of the most abundant vertebrates on the planet. The anglerfish, for example, is a classic inhabitant of this murky world. The tiny male fuses to the much larger female, living as a permanent mate and providing sperm in exchange for nutrients, a bizarre reproductive strategy unique to the deep. The female of the species famously carries a fleshy lure on her head that glows with bioluminescent bacteria. This adaptation is so effective that it inspired the design of deep-sea exploration robots. In the gloom, this small light acts as a beacon, attracting smaller fish and crustaceans towards her waiting jaws. Some prey have even evolved to recognize and avoid these deadly signals, sparking an evolutionary arms race. It is a clever and deadly trick, an adaptation born from the necessity of hunting in near-total darkness. In these depths, every meal is precious, and predators must be patient and cunning. Other creatures, like certain species of shrimp, can spew a cloud of glowing liquid to blind and confuse predators, allowing them to make a quick escape into the shadows. This bioluminescent defense is so effective that it has inspired research into new types of underwater flares and countermeasures. As we descend into the midnight zone, life becomes even more bizarre. Here, creatures like the gulper eel can unhinge their jaws to swallow prey half their size, while others, like the barrel-eye fish, have transparent heads to spot faint silhouettes above. The pressure here is so intense that animals have evolved without swim bladders, the gas-filled sacs that fish in shallower waters use to control their buoyancy. Instead, they rely on oil-filled livers or gelatinous bodies to maintain their position in the water column. Instead, their bodies are often soft and gelatinous, with watery flesh that has the same density as the surrounding water, preventing them from being crushed. The cusk eel, for example, can survive at depths over 8,000 meters. The vampire squid is a perfect example of this. Its name comes from its dark, cloak-like webbing and glowing blue eyes. It is not a true squid, but a unique creature that lives in the deep. Unlike most cephalopods, it doesn't hunt actively but feeds on marine snow, a constant rain of organic debris from above. When threatened, it doesn't release ink, but instead pulls its webbed arms over its body, creating a dark cloak, and releases a confusing cloud of glowing mucus to disorient its attacker. This remarkable defense can last up to 10 minutes, giving the squid plenty of time to vanish. In the abyssal and hadal zones, the challenges are even greater. Temperatures hover just above freezing, and the darkness is absolute. The lack of food means that life must be incredibly efficient. Amphipods, tiny crustaceans, can survive on the smallest scraps. And some have been found with plastic particles in their stomachs, showing how far human impact reaches. Many creatures are scavengers, relying on the marine snow or the occasional whale fall for sustenance. Some deep-sea worms can digest bone, extracting every last bit of nutrition. When a whale dies and its massive carcass sinks to the seafloor, it creates a temporary, rich ecosystem. Over 400 species have been documented at whale fall sites, many found nowhere else. For years, and sometimes decades, it can provide food for a succession of animals, from deep-sea sharks and hagfish to bone-eating worms called ossidacs, which have no mouths or stomachs but rely on symbiotic bacteria to digest bone. In the hadal zone itself, we have found surprisingly delicate-looking creatures like the Mariana snailfish. This fish holds the record for the deepest living fish ever filmed at nearly 8,200 meters. This small pale fish has a soft, translucent body and no scales, allowing it to withstand pressures that would turn bone to dust. Its cells contain special proteins that prevent them from collapsing under pressure. Perhaps the most astonishing discovery in the deepest parts of the trench has been the presence of giant single-celled organisms called xenophyrophores. These creatures are so fragile that they often disintegrate when brought to the surface. These creatures, which can grow to be the size of a fist, build intricate shells from sediment on the seafloor. Their complex structures provide shelter for other tiny animals, making them ecosystem engineers of the deep. They are among the largest single cells known to science and thrive in the crushing pressure and cold of the Challenger Deep. Recent studies have even found traces of plastic inside xenophyrophores, highlighting the reach of human pollution. Alongside them, communities of pale shrimp and other amphipods swarm around hydrothermal vents, which spew superheated, mineral-rich water from beneath the Earth's crust. Giant tube worms, some over 2 meters long, thrive here without mouths or digestive systems, relying on bacteria to convert chemicals into food. These ecosystems do not rely on sunlight, but on chemical energy, a process called chemosynthesis, proving that life can find a way in even the most inhospitable corners of our planet. In recent years, scientists have discovered dozens of new species at these vents, including the Hoff crab, named for its hairy chest, and unique snails with iron sulfide shells, living proof that the deep sea still holds countless secrets waiting to be uncovered. For most of human history, the deep ocean was a realm of pure speculation, a place for myths of sea monsters and bottomless pits. Ancient philosophers like Aristotle and Pliny the Elder wrote about the mysterious depths, but the technology to explore them was centuries away. The idea of actually visiting the deepest part of the ocean was science fiction, inspiring stories like Jules Verne's 20,000 Leagues Under the Sea and fueling the imaginations of early inventors. The first real steps toward deep-sea exploration began in the 1930s, when William Beebe and Otis Barton descended over 900 meters in their bathysphere, setting records and proving that humans could survive the crushing pressures of the deep. But it wasn't until 1960 that a specially designed bathyscaphe, a type of free-diving submersible called the Trieste, was prepared for the ultimate descent into the Mariana Trench. On board were Swiss engineer Jacques Piccard and US Navy Lieutenant Don Walsh, pioneers in the truest sense. They squeezed into a tiny, thick-walled steel sphere attached to the underside of the vessel, a small, fragile bubble of life in a vast, hostile sea. Their goal was to reach the bottom of the Challenger Deep, the deepest known point in the world's oceans. The descent took nearly 5 hours, a slow, tense journey into ever-increasing darkness and pressure. The crew listened as the vessel creaked and groaned under the immense strain. At one point they heard a loud crack, which turned out to be an outer plexiglass window pane fracturing under the force, a terrifying reminder of the danger they were in. Yet they persevered. When they finally touched down on the soft, silty floor of the trench, they had made history. They were the first humans to ever witness this hidden world. They spent only 20 minutes at the bottom, peering out through the tiny porthole. They saw what they described as a flatfish, proving that life could exist even at this extreme depth, before beginning their long ascent back to the world of light. For over 50 years, no human returned to the bottom of the Mariana Trench. The Trieste's feet stood alone, a testament to human ingenuity and bravery. The Trieste mission was seen as a monumental one-off achievement, like the first moon landing. The technology of the time was pushed to its absolute limits. The immense cost and danger made it seem unrepeatable. The engineering challenges were immense: pressure-resistant hulls, reliable life support, and navigation in total darkness. In the decades that followed, remotely operated vehicles, ROVs, and unmanned probes like Japan's Kaiko in 1995 reached the trench's depths, gathering valuable data and samples, but no humans. That changed in 2012 when acclaimed filmmaker and explorer James Cameron made a solo descent in a sleek, green submersible he helped design, the Deep-Sea Challenger. His mission was different. He aimed not just to reach the bottom, but to explore it. Equipped with high-definition cameras and a robotic arm for collecting samples, Cameron spent 3 hours on the seafloor, capturing stunning footage of this alien landscape and its inhabitants, revealing the trench to a new generation. These early missions were heroic and groundbreaking, but they were also isolated events. They were incredibly expensive and required years of preparation for just a few hours of exploration. They were expeditions, not sustained research. Following Cameron's dive, explorer Victor Vescovo made multiple trips to the bottom in his advanced submersible, the limiting factor, meticulously mapping the seafloor and discovering new species. These missions pushed technology forward, but the fundamental approach remained the same: send a highly specialized, expensive craft with a human pilot for a short visit. In 2012, China's Jiaolong submersible also reached the trench, marking a new era of international competition and collaboration in deep-sea exploration. A new era was dawning, however, one that would shift the focus from individual triumphs to a systematic and scalable presence in the deep. Advances in robotics, materials, science, and international cooperation are now making the Mariana Trench more accessible than ever before, promising discoveries that could change our understanding of life, Earth, and even the future of technology itself. The traditional model of deep-sea exploration, centered on rare and costly crewed missions, is rapidly being transformed by a new and ambitious player, China. In recent years, China has poured enormous resources into ocean science, signaling a strategic shift from occasional visits to establishing a persistent long-term presence in the deep. This new approach is less about heroic one-off dives and more about creating a scalable and continuous system for exploring and utilizing the ocean's depths. This change is most clearly seen in China's remarkable advancements in submersible and robotic technology, which have been developed through a combination of state-led investment, academic collaboration, and partnerships with private tech companies. In 2020, they successfully sent their own crewed submersible, the Fondouche, which means striver, to the bottom of the Challenger Deep, joining the elite club of nations capable of reaching such depths. The Fondouche itself is a marvel of engineering, equipped with advanced life support systems, high-definition cameras and robotic arms for sample collection. But China's true game-changer is not another high-tech crewed submarine. It is their focus on small, autonomous and numerous robots, autonomous underwater vehicles, or AUVs, that are revolutionizing how we explore the deep. By 2024, Chinese scientists had developed fleets of shoebox-sized robots designed to crawl along the seabed. These AUVs are equipped with sophisticated sensors, sonar, and even AI-powered navigation systems, allowing them to operate independently for extended periods. These robots are relatively inexpensive to produce and can be deployed in large numbers. Their modular design means they can be quickly adapted for different missions, from geological surveys to biological sampling. Unlike a single delicate submersible, a swarm of these robots can work together to map vast areas of the seafloor, collect samples, and monitor the environment continuously. Their collective intelligence allows them to coordinate tasks, avoid obstacles, and share data in real time. They can be left to work for months at a time, sending back a constant stream of data. Advanced communication systems relay information to surface buoys and satellites, enabling scientists to monitor conditions and make adjustments remotely. This represents a fundamental change from sending a human for a few hours to having a tireless robotic workforce operating around the clock. The impact is profound. Scientists can now gather long-term data on deep-sea ecosystems, track changes over time, and respond rapidly to new discoveries. The ambition does not stop with robotic swarms. China is investing in next-generation AUVs with advanced AI capable of making decisions on the fly, repairing themselves, and even collaborating with other robots to complete complex tasks. China is already making plans for what could be described as an international space station for the deep sea, a permanent modular base that would serve as a hub for both human and robotic operations. They have announced a project to build a permanent crewed underwater base at a depth of 2,000 meters. This facility will be equipped with docking bays for AUVs, laboratories and living quarters for scientists. This habitat would be designed to house a team of 6 scientists for up to 30 days at a time, allowing for long-term experiments and direct observation in the deep-sea environment. The integration of human expertise and robotic labour will enable unprecedented research opportunities. Such a facility would be an unparalleled platform for scientific research, giving China a permanent foothold in a realm that has, until now, only been visited fleetingly. It would be a hub from which they could deploy their robotic fleets and control operations across the region. The seamless integration of robotics and human oversight will maximize efficiency and safety in deep-sea missions. This rapid progress is fueled by a massive national commitment. China has established dedicated research centers for marine robotics, where engineers and scientists work side by side to push the boundaries of underwater technology. While other countries have seen funding for oceanographic research fluctuate or even decline, China is building new state-of-the-art ocean science laboratories and actively recruiting top scientific talent from around the world. This focused investment is creating a brain drain from other nations as leading researchers move to where the funding and opportunities are greatest. International collaboration is also accelerating the pace of innovation, as Chinese teams work with global partners to develop next-generation sensors, batteries and AI systems for underwater use. China's strategy is clear. They are not just aiming to catch up in deep-sea exploration, they are aiming to become the world's undisputed leader, transforming our relationship with the deep ocean from one of brief visits to one of permanent occupation. Through relentless innovation in robotics, China is redefining what is possible beneath the waves. The intense international interest in the deep sea, particularly from industrial powers like China, is not driven by scientific curiosity alone. Instead, it is fueled by the immense economic and strategic potential hidden beneath the waves. The abyssal plains and hydrothermal vents of the deep ocean are home to vast, untapped deposits of valuable resources, creating the prospect of a 21st century gold rush. These resources are not only critical for global industry, but also for the technological ambitions of nations seeking to secure their economic futures. One of the most significant prizes are polymetallic nodules, small, rock-like formations that could transform the global supply of essential metals. These are potato-sized, rock-like concretions that lie scattered across the seafloor in certain areas, especially in regions like the Clarion-Clipperton Zone, where China has already secured exploration rights. They are formed over millions of years as minerals from the seawater slowly precipitate around a central core, like a pearl forming in an oyster. This slow process results in nodules rich in metals that are increasingly scarce on land. These nodules are rich in metals that are crucial for our modern green tech economy, including the transition to renewable energy and electric vehicles. These unassuming black rocks contain high concentrations of cobalt, nickel, copper and manganese, metals vital for batteries, electronics and clean energy infrastructure. These are the very metals needed to build batteries for electric cars, components for wind turbines and electronics for smartphones and computers. As the world races to decarbonize, demand for these resources is skyrocketing. As the world transitions away from fossil fuels, the demand for these metals is soaring, and land-based mines are struggling to keep up. Deep-sea mining offers a potential solution, but also raises questions about environmental impact and global competition. The deep sea, therefore, represents a massive untapped source. For China, which is the world's largest consumer and processor of many critical minerals, securing access to these resources is a top priority. The process of harvesting them would involve large robotic vehicles like underwater tractors crawling along the seafloor, scooping up the nodules and sending them to a surface ship through a giant pipe. China has invested heavily in developing these technologies, aiming to become a leader in deep-sea mining. For nations looking to secure their supply chains for future technologies, controlling these deposits is a major strategic goal. China's deep-sea ambitions are part of a broader strategy to reduce dependence on foreign sources and dominate the global market for high-tech materials. Another potential resource is a strange substance known as methane hydrate, or fire ice, a material that could revolutionize the global energy market. This is a solid ice-like material where methane gas molecules are trapped within a crystal lattice of frozen water. Methane hydrates are found in abundance beneath the seafloor, especially in the South China Sea, where China has conducted successful extraction trials. It forms under the high-pressure, low-temperature conditions found in deep-sea sediments. The potential energy stored in these deposits is staggering. When brought to the surface, it is unstable and can be lit on fire, releasing the trapped natural gas. This makes methane hydrate both a promising energy source and a technical challenge. The amount of energy stored in fire ice deposits around the world is thought to be immense, potentially exceeding all other known fossil fuel reserves combined. For China, which faces growing energy demands, unlocking this resource could be a game changer. For energy-hungry nations, it represents a tantalizing future fuel source, although the technology to extract it safely and economically is still in its infancy. China's government has made deep-sea energy research a national priority, investing in both scientific and commercial ventures. Beyond minerals and fuel, the deep sea holds other valuable secrets, many of which are only beginning to be understood by science. Around hydrothermal vents and cold seeps, areas where chemical-rich fluids leak from the seafloor, unique ecosystems thrive. These environments are of immense scientific interest, offering clues to the origins of life and the potential for new biotechnologies. The bacteria and other organisms that live here have evolved to survive in extreme conditions of temperature and toxicity. Their unique adaptations could inspire new medicines, materials, and industrial processes. Scientists believe that studying these extremophiles could lead to breakthroughs in medicine, such as new antibiotics or industrial applications, like enzymes that can function in harsh manufacturing processes. China's deep-sea research programs are actively exploring these possibilities, hoping to gain a competitive edge in biotechnology. The genetic information contained within these unique life forms is itself a valuable resource, a biological treasure chest that is only just being opened. The potential for scientific discovery is as vast as the ocean itself. The race to the deep is therefore a race for minerals, for energy, for scientific breakthroughs, and for the very building blocks of life. For China and other ambitious nations, the deep sea is both a frontier of economic opportunity and a laboratory for the future. The prospect of unlocking the immense wealth of the deep sea comes with a profound environmental cost. Around the world, scientists, policymakers and environmentalists are locked in heated debate over whether the risks are simply too great. The ecosystems of the deep ocean are among the most fragile and slow-growing on Earth. Many species found here are unknown to science, and some may hold secrets vital to medicine or biotechnology. These habitats have remained stable and undisturbed for millions of years, and the life that exists there is uniquely adapted to a world of darkness, silence and stillness. Some creatures, like the ghost octopus or the yeti crab, are found nowhere else on Earth. The industrial-scale disruption that would be caused by deep-sea mining could inflict damage that would take centuries or even millennia to heal, if it ever heals at all. In some test sites, scars from experimental mining decades ago are still visible, with little sign of recovery. The primary method for harvesting polymetallic nodules, for instance, involves scraping the top layer of the seafloor with large robotic vehicles. This is not a surgical operation, it is more like clear-cutting a forest, but in the dark depths. This process would destroy the habitat completely, crushing or burying any life in its path. The most immediate impact of this mining would be the creation of large sediment plumes, which can suffocate life far beyond the mining site itself. As the mining machines scoop up nodules, they will kick up vast clouds of fine mud and sand from the seafloor. These clouds can travel for many kilometers, blanketing everything in their path. This sediment can travel for many kilometers, blanketing everything in its path. In some cases, plumes have been observed spreading far beyond the intended mining area, impacting sensitive habitats. For the delicate filter-feeding organisms that live on the seabed, like sponges and sea anemones, this blanket of mud would be catastrophic, smothering them and cutting off their food supply. Some species may never recover. These plumes would also spread through the water column, potentially harming creatures living far from the actual mining site. Migratory species, like certain fish and squid, could be affected as they pass through these disturbed zones. Because the deep sea is such a still environment, this sediment could remain suspended for years, creating a persistent fog that chokes out life. In some regions, scientists worry that entire food webs could collapse. The extraction of fire ice or methane hydrate poses its own unique and significant risks. Methane hydrates are highly unstable, and disturbing them can have unpredictable consequences. These deposits are often what holds the sediment on underwater slopes together. Removing them could trigger landslides on a massive scale. Disturbing them could destabilize the seafloor, potentially triggering massive underwater landslides. In the worst-case scenario, these landslides could generate tsunamis that threaten coastal communities, as seen in past geological events. Such landslides could, in a worst-case scenario, generate tsunamis that could threaten coastal communities. The risk is not just theoretical. Scientists have documented similar events in Earth's history. Furthermore, there is a serious risk of releasing large quantities of methane directly into the ocean and atmosphere. Methane is a far more potent greenhouse gas than carbon dioxide. A sudden large-scale release could have a devastating impact on our climate, accelerating global warming. Some experts warn that this could undermine efforts to limit global temperature rise. The promise of a new energy source could come at an unacceptable environmental price. Around the world, environmental groups are calling for a moratorium on deep-sea mining until more is known. Because we know so little about the deep sea, we cannot fully predict the long-term consequences of our actions. The International Seabed Authority is under pressure to balance economic interests with environmental protection. The life forms in the deep grow incredibly slowly. Some deep-sea corals are thousands of years old. Recovery, if it happens at all, could take longer than human civilization has existed. The ecosystems are connected in ways we are only just beginning to understand. Disrupting one area could have ripple effects across vast distances. Destroying a hydrothermal vent community or a field of polymetallic nodules is not like cutting down a forest that might one day regrow. Some species may be lost forever, before we even have a chance to study them. It is more like destroying an ancient city and its library of unique knowledge forever. The genetic diversity and evolutionary history stored in these habitats is irreplaceable. Before we rush to exploit these resources, many scientists argue that we need a global pause, a period of intense research and international cooperation to understand what we stand to lose. The world is watching, and the choices we make now will echo for generations. Hidden from view on the quiet floor of the deep ocean lies the true backbone of our modern, interconnected world. Beneath thousands of meters of water, a web of undersea cables stretches for over 1.3 million kilometers, enough to circle the Earth more than 30 times. These cables are not made of satellites or radio waves, but of delicate garden hose-sized fiber-optic lines, each containing hundreds of glass strands thinner than a human hair. Through these strands, pulses of light carry the world's information at nearly the speed of light. Over 99% of all international internet traffic, emails, financial transactions, video calls, streaming and even military communications travels through this undersea network. Every second, trillions of dollars in value and billions of private messages cross the globe, relying on these hidden arteries. These cables are the physical manifestation of the internet, the lifelines that connect continents, economies and societies. Without them, the globalized world, as we know it, would grind to a halt in an instant. They are essential for global trade, banking, and communication. Stock markets, international payments, and even the coordination of emergency services depend on the uninterrupted flow of data through these cables. If these cables were to fail, the impact would be immediate and severe. Financial markets would freeze, businesses would be unable to operate, and entire populations could be cut off from the outside world. Yet despite their importance, this critical infrastructure is incredibly vulnerable. For the most part, these cables simply lie on the seabed, exposed and unprotected. especially in the deep ocean where burial is impossible. While they are sometimes buried in shallow coastal areas to protect them from human activity, across the vast open stretches of the deep sea they are left open to the elements and to risk. Most damage to these cables is accidental. Fishing trawlers dragging heavy nets, ship anchors dropped in the wrong place, and even natural disasters like underwater landslides or volcanic eruptions can snap these fragile lines. When a cable is cut, it can disrupt internet services for entire regions, as seen in places like Taiwan, Egypt, and parts of Africa. Outages can last days or even weeks, with ripple effects on economies and daily life. Repairing a broken cable is a slow, complex, and expensive process. Specialized ships must locate the break, grapple for the cable ends on the sea floor, haul them to the surface and carefully splice them back together, sometimes in treacherous weather and remote locations. But accidental damage is only part of the story. The growing competition for control of the deep sea introduces a new and more sinister threat: deliberate sabotage. A nation with advanced deep-sea capabilities could covertly disable an adversary's communication systems without firing a single shot. The ability to precisely locate and cut these critical cables would be a powerful strategic weapon, capable of creating confusion and paralysis in the lead-up to conflict. In early 2025, it was revealed that China had developed a deep-sea robot specifically designed as a cable cutter. While it was officially presented as a tool for repairs, its existence immediately raised concerns among security experts worldwide. Such a machine could be used to quietly sever an enemy's data links, leaving entire countries in the dark and unable to coordinate a response. The threat is not just theoretical. Military planners now consider undersea cables a prime target in any future conflict. The vulnerability of these cables highlights the immense strategic importance of controlling the deep ocean. The nation that can dominate this environment can not only protect its own undersea infrastructure, but also threaten that of others. This is a new form of warfare, one that could be waged silently and invisibly in the dark depths, far from the public eye. The ability to map, monitor, and operate on the seafloor is becoming as important as controlling the skies or the sea's surface. As global data traffic continues to grow exponentially, and as more critical infrastructure, like energy pipelines and power cables, joins the undersea network, the stakes are only getting higher. The global network that we all depend on for our daily lives rests on a fragile foundation. The race to the deep is also a race to control the switches that keep our world running, and the risks posed by deep-sea activities, both accidental and intentional, are greater than ever before. The deep ocean, and the Mariana Trench at its heart, represents far more than just a new frontier for scientific discovery or resource extraction. It is a vast, interconnected system that underpins the health, stability and future of our entire planet. It is a fundamental part of our planet's life support system, influencing everything from the air we breathe to the food we eat and the climate we experience. The vast, dark waters of the abyss play a crucial role in regulating our global climate, absorbing heat and distributing energy around the world through powerful currents. The ocean absorbs enormous amounts of heat and carbon dioxide from the atmosphere, and the deep sea acts as a long-term storage facility for both. Without this, our planet would be far hotter and less hospitable. The process of marine snow, the slow drift of organic matter to the seafloor, effectively locks away carbon for thousands of years, helping to keep our planet's climate stable. This natural carbon sink is vital in the fight against climate change. Disturbing these deep-sea systems on a large scale could have unforeseen consequences for the air we breathe, the stability of our climate, and the health of marine ecosystems that support life on Earth. Protecting this remote and mysterious realm is a responsibility that falls to all of us, not just scientists or policymakers, but every individual who depends on a healthy planet. The deep sea does not belong to any single nation. It is a shared heritage of humanity, governed by a complex set of international laws like the UN Convention on the Law of the Sea. Its stewardship requires global cooperation and mutual respect. However, as technology advances and the strategic and economic stakes grow higher, these laws will be tested. The deep sea is rich in rare minerals and metals essential for modern technology, from smartphones to renewable energy systems. The rush to mine the seabed, the competition for strategic dominance, and the potential for environmental disaster require us to act with foresight and caution. Economic opportunity must be balanced with environmental responsibility. We must work together as a global community to establish strong, enforceable rules for the exploration and use of the deep ocean before irreparable damage is done. International collaboration is essential to ensure both prosperity and preservation. Our journey into the deep is in many ways a reflection of our journey as a species. It is a story of curiosity, ambition, and the search for understanding. It is driven by our innate curiosity, our desire to explore the unknown, and our quest for knowledge. The deep sea holds secrets about the origins of life, the limits of biology, and the resilience of ecosystems under extreme conditions. But it is also driven by our hunger for resources and our competition for power. The minerals found here are critical for the green technologies that will shape our future, but extracting them could come at a high environmental cost. The choices we make about the deep sea in the coming decades will say a lot about our wisdom and our ability to act as responsible stewards of our planet. Will we prioritize short-term gain or long-term sustainability? Will we treat the deep ocean as just another resource to be exploited, leaving a trail of destruction in our wake? The consequences of mismanagement could be catastrophic, not just for marine life, but for humanity itself. Or will we approach it with the respect and awe that such a wondrous and vital part of our world deserves? Education and awareness are key to inspiring the next generation of ocean stewards. The Mariana Trench and the dark zones below it are the last truly wild places on Earth. They remain largely unexplored, holding mysteries that could transform our understanding of life and the planet. They are a world of crushing pressure, strange life, and silent beauty. Every expedition uncovers new species and adaptations, expanding the boundaries of science and medicine. They hold the answers to scientific questions we have not yet thought to ask and contain resources that could shape the future of our civilization. Deep-sea organisms may hold the key to new medicines, materials, and technologies. As we stand at the edge of this abyss, with new technologies like China's robotic fleets ready to plunge in, we must remember that it is not an empty void, but a living, breathing part of our world. The deep sea connects nations, economies, and ecosystems. Its future, and in many ways our own, depends on the choices we make today. The path we choose will determine whether the deep sea remains a source of wonder and life, or becomes a cautionary tale of lost opportunity. We must explore, we must learn, but above all, we must protect. The deep sea matters to us all, environmentally, economically, and scientifically. Its fate is in our hands. Beneath the crushing pressures and perpetual darkness of the Mariana Trench, borders disappear. Here, the pursuit of knowledge demands a spirit of collaboration that transcends nationality and politics. International partnerships have become the backbone of deep-sea research, uniting scientists, engineers, and explorers from around the world. Joint missions, like those between the United States, Japan, and China, have made it possible to share the immense costs and technical challenges of exploring the planet's most inaccessible depths. These collaborations pool cutting-edge technology, research vessels, and expertise, allowing for more ambitious discoveries than any one nation could achieve alone. Data sharing is another cornerstone of global cooperation. The vast amounts of information gathered from mapping the seafloor to cataloguing new species are shared through international databases, open access journals, and scientific conferences. This transparency accelerates breakthroughs, avoids duplication, and ensures that knowledge about the deep ocean benefits all of humanity. But working together in the Mariana Trench is not without its challenges. Differing national interests, proprietary technologies, and political tensions can complicate even the most well-intentioned partnership. Negotiating access, aligning research goals, and respecting each nation's contributions require diplomacy and trust. Yet the rewards are profound. Every joint expedition is a testament to what humanity can achieve when united by curiosity and respect for our planet. As we look to the future, fostering these global partnerships will be essential, not only to unlock the mysteries of the deep, but to ensure that its wonders and resources are protected for generations to come. As we stand on the threshold of a new era in deep-sea exploration, the technologies guiding our journey are evolving faster than ever before. Artificial intelligence is at the helm of a revolution beneath the waves, powering submersibles that can navigate the crushing depths autonomously, analyzing data, avoiding hazards, and even making discoveries without human intervention. Advanced sensors are now capable of detecting the faintest chemical traces, mapping the ocean floor in unprecedented detail, and capturing high-resolution images in total darkness. These innovations are transforming how we study deep-sea ecosystems, revealing hidden worlds that were invisible just a decade ago. Remote-operated vehicles, or ROVs, are becoming more agile and robust, tackling complex tasks miles below the surface. Equipped with precision robotic arms and real-time communication links, they can collect samples, repair undersea cables, and even build infrastructure on the ocean floor, all while keeping human operators safe above the waves. Researchers are also experimenting with swarms of miniature robots, working together like schools of fish to cover vast areas quickly and efficiently. These fleets could one day monitor the health of our oceans, track elusive species, or respond to environmental threats as they emerge. With each new innovation, the mysteries of the Mariana Trench and the deep sea come into sharper focus. The future of exploration is not just about going deeper, it's about seeing more, understanding more, and protecting more than ever before. The next chapter in our journey beneath the waves is only just beginning. Beneath the crushing darkness of the Mariana Trench lies more than just an unexplored world. It holds clues to some of our planet's greatest mysteries. By studying the trench, scientists gain valuable insights into how the ocean shapes our climate, the movement of currents, and the delicate balance of the Earth's carbon cycle. Deep-sea sediments act as time capsules, preserving evidence of past climate shifts and offering a window into how our planet has changed over millions of years. By analyzing these layers, researchers can track ancient carbon flows and understand how the deep ocean stores and releases this vital element, influencing global temperatures. The trench's unique geography also affects how water travels around the globe. Powerful currents sweep through its depths, helping to drive the circulation patterns that regulate heat and nutrients across the oceans. By mapping these pathways, scientists can predict how changes in the deep sea might ripple out to impact weather, fisheries, and even the air we breathe. Ultimately, exploring the Mariana Trench isn't just about satisfying human curiosity. It's about unlocking the secrets that connect the ocean's deepest realms to the future of life on Earth. As technology opens the door to the ocean's deepest frontiers, new challenges emerge, ones not just of science, but of law and ethics. The Mariana Trench and much of the deep sea lie in international waters far beyond the jurisdiction of any single nation. Here, the United Nations Convention on the Law of the Sea, or UNCLOS, sets the rules for exploration and resource use. Yet as interest in deep-sea mining and extraction grows, so do the debates. Who truly owns the riches hidden in the abyss? UNCLOS declares the deep seabed the common heritage of mankind, meant to be used for the benefit of all. But enforcing these ideals is complex. The International Seabed Authority oversees mining contracts and aims to balance economic opportunity with environmental protection. But critics argue that loopholes and limited oversight put fragile ecosystems at risk. Ethical questions loom large. Should we risk disturbing ancient habitats for minerals? How do we ensure that developing nations and future generations share in the benefits? And what rights do deep-sea creatures have in this equation? As we push further into the unknown, the need for robust global cooperation and clear ethical standards has never been greater. The choices we make today will shape the fate of the deep sea and the legacy we leave beneath the waves.